This image took the Hubble Space Telescope days of staring at one tiny, dark patch of sky to capture. Thousands of galaxies, each holding billions of stars, packed into a spot you could cover with a single grain of sand held at arm's length. Think about that for a moment. Every one of those smudges is an entire island universe, and they were all hiding in a piece of sky most people would call empty. It's one of the most famous photographs in human history, and it fundamentally changed how we see our place in the cosmos. Before it, that patch of sky looked like nothing. After it, we understood that nothing, anywhere, is truly empty. Now imagine a telescope that captures that exact same crisp detail, but across a patch of sky 100 times larger, all in a single shot. Not blurrier, not lower quality. The same razor sharpness, spread across 100 times the area at once. A telescope that can sweep across the entire sky so quickly that it will finish, in just a few months, work that would take Hubble literally hundreds of years to complete. This is not science fiction, and it is not decades away. It's called the Nancy Grace Roman Space Telescope, and it is scheduled to launch on August 30th, 2026, just weeks from now. By the time its main mission is finished, it will have mapped more than 1 billion galaxies, discovered over 100,000 new planets, and possibly cracked the single biggest unsolved mystery in all of physics. And yet, if you stopped 10 people on the street, almost none of them would have heard its name. So let's fix that right now. Stick with me all the way through, because the scale of what this machine is about to attempt is genuinely difficult to wrap your head around. I'm going to keep translating these impossible numbers into things you can actually feel, and by the end, you'll understand exactly why astronomers are calling Roman a once-in-a-generation game-changer for the entire science of the universe. This is one of those rare moments where the tool is so far ahead of everything before it that it doesn't just answer old questions, it invents entirely new ones. First, the basics. Roman is NASA's next great flagship observatory, the biggest space astronomy launch since James Webb lifted off. It's named after Nancy Grace Roman, NASA's very first chief astronomer and the first woman ever to hold an executive role at the agency. She's often called the Mother of Hubble because she fought to make that mission a reality, back when it was still just an idea nobody would fund. It's fitting that the telescope carrying her name is the one built to pick up where Hubble left off, and then go far beyond it. Roman spent decades being told that a big orbiting telescope was too expensive, too risky, too ambitious to ever fly, and she kept pushing anyway. Without her stubbornness, some of the most iconic images in human history might never have existed. So, in a very real sense, this launch is her legacy taking flight one more time. When it's fully deployed, Roman stretches about 12.7 meters long, roughly the length of a semi-truck trailer, and weighs around 8,000 kilograms, close to 18,000 pounds before fuel. At its heart sits a primary mirror, 2.4 meters across. And here's the first surprising twist of this whole story. That mirror is exactly the same size as Hubble's. In fact, part of Roman's optics came from hardware originally handed to NASA by the National Reconnaissance Office, the agency that builds America's spy satellites. So, if the mirror is the same size as the one on Hubble, how on earth does Roman see 100 times more sky at once? Hold on to that question, because the answer is the entire reason this telescope exists. Roman is launching aboard a SpaceX Falcon Heavy, currently the most powerful operational rocket in the world, lifting off from Launch Complex 39A, the same historic pad that once sent the Apollo astronauts toward the moon. And here's something almost unheard of in modern spaceflight. Roman is arriving early. NASA moved the launch up by roughly 8 months, well ahead of its original readiness deadline. Big space telescopes are notorious for the opposite, running years behind schedule and billions over budget. Webb famously did. Roman, somehow, showed up to the launch pad ahead of time and under control. That alone tells you this program has been run with unusual discipline. After it launches, Roman will cruise out to the second Lagrange point, known as L2, the same gravitationally stable parking spot that Webb uses. It sits about 1.5 million kilometers from Earth, roughly 4 times farther away than the Moon. Out there, the gravity of the Sun and the Earth balance in a way that lets a spacecraft hold its position with very little fuel, in the cold, steady dark that infrared telescopes need. It's about the loneliest, most stable address in the neighborhood of Earth, the perfect place to sit still and watch the whole sky. Then, after several months of careful commissioning and calibration, the real work finally begins. To really understand why Roman is special, you have to see how it differs from the 2 telescopes you already know by name. And the cleanest way to picture it is like this. Hubble is like a superb microscope. It takes breathtakingly detailed pictures of small areas of sky. Webb is an even more powerful microscope, reaching for fainter, more distant, colder objects in infrared light. Both of them stare deep and narrow, drilling down into tiny slivers of the heavens. Roman does almost the exact opposite. Roman is a wide-angle survey camera. Instead of photographing one street corner in perfect detail, it photographs an entire city block at once, and everything in that frame is just as sharp. So here, at last, is the answer to that riddle from a minute ago. Same mirror, same sharpness. But Roman's camera captures a field of view at least 100 times larger than Hubble's in every single exposure. It isn't seeing better than Hubble, it's seeing wider. And that difference sounds small until you realize what it unlocks. When you can see that much sky at once, without giving up any detail, you stop studying the universe one galaxy at a time. Instead, you start capturing millions of them in a single frame. It lets Roman survey the sky up to 1,000 times faster than Hubble ever could. Put it another way, a survey that would swallow hundreds of years of Hubble's precious observing time, Roman can knock out in a matter of months. It's the difference between mapping a country one backyard at a time and photographing the whole thing from orbit in an afternoon. The engine that makes this possible is an instrument called the Wide Field Instrument, a roughly 300 megapixel infrared camera built from 18 separate detectors, each one capturing about 16 million pixels.
Alignment looks good.
It is one of the largest cameras ever flown into space, and it's finely tuned to see near infrared light, the kind of light that slips straight through clouds of cosmic dust and reveals the most distant, most ancient objects in the universe, the ones whose light has been stretched and reddened by billions of years of cosmic expansion. Roman also carries a second tool, a coronagraph, designed to block the blinding glare of a star so we can photograph the faint planets orbiting around it. Here's a way to actually feel that difference in your gut. To photograph the entire Andromeda galaxy, Hubble has to painstakingly stitch together thousands of separate images captured over years of observing time. Roman can capture that same enormous region in just a small handful of shots. That single leap in speed is the whole story of this mission, because speed is exactly what transforms astronomy from carefully studying individual objects into mapping the entire universe at once. So what do you actually do with a telescope this fast? You point it at the biggest questions humanity has ever asked. And mission number 1 is a genuine doozy. Over its 5-year primary mission, Roman is expected to observe more than 1 billion galaxies. And I don't mean glance at 1 billion galaxies loosely. I mean survey them, precisely measuring their shapes, their distances, and the way they clump and cluster together across the vast sweep of cosmic time. 1 billion galaxies, plus tens of billions of individual stars on top of that. Let that number really settle for a second. Roman will catalog more galaxies than there are human beings on Earth, several times over. But this is not just about assembling the biggest, prettiest picture ever taken. The real point of all that mapping is to hunt down an invisible monster. Here's the mystery that keeps physicists up at night. The universe isn't just expanding, its expansion is actually speeding up, accelerating over time. Something is pushing the cosmos apart harder and harder, and we genuinely have no idea what it is. We've given it a placeholder name, dark energy, and by our best estimates, it makes up roughly 68% of everything that exists. We cannot see it, we cannot touch it, and we cannot explain it. It is, arguably, the single biggest unsolved problem in all of physics, and it's sitting inside every cubic inch of empty space around you right now. To picture how strange this is, imagine throwing a ball into the air, and, instead of slowing down and falling back, it speeds up and flies away, faster and faster. That's essentially what the entire universe is doing, and nothing in our everyday understanding of gravity explains why. Roman goes after this in a few clever ways at once. By mapping how the light from hundreds of millions of galaxies is subtly warped and bent by the gravity of everything in front of it, and by tracking a special kind of exploding star called a Type 1a supernova, which always detonates with nearly the same brightness, making it a reliable cosmic distance marker. Roman can measure precisely how fast the universe has been expanding at many different points across its history. Stitch all of that together, and you get something extraordinary. A detailed map that is essentially the fingerprint of dark energy itself. And the results could go one of two ways. They might confirm our best current theories and tighten them up, or they might contradict them completely and force physicists to rewrite the rulebook of the cosmos from scratch. Okay, mapping the entire universe is one thing, but Roman's second job might honestly be even wilder. It's going to hunt for planets, and not a modest handful of planets. Estimates suggest Roman could discover more than 100,000 exoplanets using the transit method alone, plus over 1,000 more through a second, stranger technique. If those numbers hold, it would be the largest single planet hunting haul in the history of astronomy, potentially rivaling every planet found by every other mission combined. Roman finds these worlds in two main ways. The first is the transit method, patiently watching for the tiny, regular dip in a star's brightness that happens when an orbiting planet passes directly in front of it, blocking a sliver of its light. It's a proven technique. But the second method is the truly mind-bending one, and it's where Roman really shows off: gravitational microlensing. Microlensing uses gravity itself as a magnifying glass. When one star happens to pass almost perfectly in front of a more distant star, the closer star's gravity bends and focuses the far star's light, briefly making it flare up brighter. And here's the beautiful part. If that closer star has a planet orbiting it, the planet's own gravity adds a tiny extra flicker on top of that brightening, a little spike within the spike. Roman will stare directly into the crowded, star-packed heart of our own galaxy, quietly monitoring hundreds of millions of stars at once, watching for exactly these fleeting signatures. And here's the part that gives away just how new this really is. Microlensing can detect worlds that every other method on Earth completely misses. Small, rocky, Earth-mass planets in wide, distant orbits, and even so-called rogue planets, free-floating worlds drifting alone through the galaxy, bound to no star at all, lost in permanent darkness. Roman may uncover hundreds of these cosmic orphans, planets the size of Earth wandering through interstellar space with no sun to warm them. Worlds we'd have almost no other way of ever finding. Taken together, all of this adds up to something we've never had before: the first true census of the planets in our galaxy. For the first time, we'll be able to seriously answer whether solar systems like our own are common across the Milky Way, or whether we are genuinely rare. Now step back for a second, because Roman isn't arriving on the scene alone. It's the crown jewel of a brand new era in astronomy. Down in the mountains of Chile, the Vera Rubin Observatory has begun filming what people are calling the greatest cosmic movie ever made, scanning the entire southern sky over and over, night after night. Over in Europe, the Euclid mission is already mapping billions of galaxies for the very same dark energy hunt. Together, these machines are quietly transforming astronomy from a science of individual, one-off discoveries into a science of complete, all-encompassing maps. And that is the real reason Roman is so genuinely insane. It isn't simply a better telescope than the ones before it. It's a fundamentally different kind of tool. For the first time in history, we won't only be asking, what does this one particular object look like? We'll be asking something far grander. What does the entire universe look like, all at once, all together? And the sheer flood of data these surveys produce will fuel new discoveries for decades to come, including things nobody has even thought to look for yet. In fact, some of Roman's most important discoveries almost certainly aren't written on anyone's mission plan today. They're waiting, hidden inside data that simply hasn't been collected yet. Roman will beam back an almost unimaginable flood of information, so much that no team of humans could ever sift through it by hand. Scientists will lean on automated pipelines and machine learning just to keep up, and the archive it leaves behind will still be delivering brand new discoveries long after the telescope itself has gone quiet. Just think about the moment we're standing in. In a matter of weeks, we are going to place a machine 1.5 million kilometers from Earth that will photograph 1 billion galaxies, uncover 100,000 brand new worlds, and stare directly at the invisible force that is tearing the entire cosmos apart. And most people, scrolling past the headlines, won't even glance at it. But you will. You'll know exactly what's happening up there and why it matters. When we started this video, one grain of sand patch of sky held thousands of galaxies. Roman is about to do exactly that, across the whole sky, and in the process, change what we ever thought was even possible to know about the universe we live in. Launch is targeted for August 30th. After that comes several months of setup and calibration. And then, slowly at first, and then all at once, the maps start rolling in. And once they do, our view of the universe simply won't be the same. We'll have gone from squinting at single galaxies to holding a map of 1 billion of them in our hands. If you want to actually understand these images when they arrive, instead of just scrolling right past them like everyone else, subscribe, and I'll break down Roman's very first discoveries the moment they drop. And go check out the video on screen right now about the interstellar visitor that broke every rule of physics we had. Thanks for watching, and as always, keep looking up, because the sky is about to get a whole lot bigger.